Okay, folks. Uh, yeah, let's continue and talk about the half-wave plate. One second. Okay, a moment ago we considered a birefringent material and showed that you can use a birefringent material to produce a phase shift between vertical and horizontal components of light that cross the crystal. It's a little complicated, but now that we've done that, a half-wave plate is a birefringent plate which is just thick enough so that for a specific wavelength, the phase shift will be pi, okay? Phase shift of pi, that's a half-wave plate. And now let's see what happens when light crosses a half-wave plate. Let's assume that we have light of a certain linear polarization, which is polarized at an angle theta relative to our half-wave plate. The half-wave plate looks like a polarizer here, but it's not, it's a half-wave plate, not a polarizer. And here, the vertical line indicates the direction of the extraordinary axis of the polarizer, okay? So let's see if light of linearly polarized at an angle theta crosses this half-wave plate, what will be the polarization state afterwards? That's the question we're going to answer. Actually, this isn't hard to solve. We can solve it graphically more easily than we can solve it algebraically, and I'm for that. So let's take a look, okay? Here's the idea. Originally, our light beam had a polarization at an angle theta with respect to the vertical, okay? Or with, we're picking out the vertical as the special direction, okay? Now, what we should do in order to analyze this is we should then resolve this vector into a component parallel to the birefringent plate and to the component perpendicular to the birefringent plate. There we are. Now, what we expect is that the half-wave plate will induce a phase shift of 180 degrees, or pi, between these two components. So that after we've passed through the plate, we'll find the following. The component parallel to the optical axis might be unchanged, but then relative to that, the component perpendicular to the optical axis will be shifted in phase by 180 degrees, by pi radians, which is equivalent to changing the sign. Oops. And that's because, remember, these vectors are oscillating in time, and delaying it by by pi radians, or half a period, means taking it from a positive component to a negative component. So we've changed the sign of one of the components, but not the other. Now we can reconstruct the resultant vector. There it is. And you can see right away that if the original angle was theta, the new angle will be minus theta. Okay? So the new polarization angle will be minus theta. And that's what the half-wave plate does. To sum up then, the half-wave plate produces a shift in the polarization angle of the light that depends on the incidence angle, the angle between the polarization of the light and the orientation of the half-wave plate. If the orientation difference is 0, then of course the shift in polarization direction will be 0. But if the polarization angle, if the initial angle is something else, excuse me, like 10 degrees, then the shift will be twice that. It'll be 2 theta, so it'll be 20 degrees, okay? And going on a couple special cases, if we arrange for the polarization to be 22.5 degrees away from the angle of the half-wave plate, then the polarization will be rotated by 45 degrees. And if it's 45 degrees, the shift will be 90 degrees, which is pretty neat. We would change the light from one polarization to an orthogonal polarization. Finally, if we did, let's say, 90 degrees, the shift would be 180 degrees, which actually, from our point of view, is like no change at all, because we're taking light that's oriented vertically and shifting it into light that's still oriented vertically, even if there is a 180 degrees change, it doesn't end up changing the polarization direction. So that's what a pathway plate does, is it rotates the polarization of linearly polarized light. It's a very useful trick, and so that's what half-wave plates are for. Okay, and I'll give you a little problem, and then we'll be done with this section.